Welcome to the second talk in this session. Let's welcome our speaker, Olga Dyaszewska, who will now show us how to track birds using radar and Python. Join me in welcoming Olga with a warm applause.
Thank you very much. I didn't realize that many people were interested in birds, but here you go. So today I would like to talk about using GNNs, which is graph neural networks, for identification of objects with meteorological radars. Out of curiosity, I don't have a Mentimeter, but I want to know how many of you are using GNNs or have any knowledge of, so that I can... I didn't expect, by the way, but just to know. So apologies if it's too boring for you guys, it will be very basic. But hopefully tools we develop will be of some use to some of you, or at least a concept so that you can apply to your own work. And a kind of abbreviation for this project is where is the flock. I hope you can see a hidden meaning there. We didn't want to abbreviate it too much, but so WTF, because we were so fed up with it. Anyways, I will talk here on behalf of my colleagues who are not here at the moment. This project is a collaboration with University of Amsterdam. And I'll give you a short slide on myself, just in case you have similar interests, we can link up and follow up. So I work as a research software engineer in eScience Center in the Netherlands. I'll have a slide on that, just in case, because we are an open organization, we welcome new projects from new people. It's absolutely free, so maybe some of you will be interested. Before that, I've been about 7 years in Ireland on the West Coast. I worked at university. And my domain was kind of broad from environmental sciences with my medical and engineering technologies on the programming side of it. I have some expertise in statistics, machine learning, and I am a Linux enthusiast with over 15 years of use, so this is my hobby. So just a brief information about organization, because I think it's quite nice. So we are independent national center. We are funded by taxpayers. And what we do, we provide solutions to scientists. Okay, so anybody who is postdoc level or above with an interesting research problem which requires computational resources or programming solutions or software which should be open can apply, and it's absolutely of no cost to you if your project is approved. So we kind of have two ambitions here. First of all would be to collaborate with scientists and design software for research, which is very interesting. And the second ambition would be to build a digital expertise by organizing trainings and courses. So I think this is quite similar to the previous speaker, as far as I understand, because they also provide solutions for scientists. And this project I'm presenting is just one of the projects we do, and we have a whole wide variety of projects from environmental sciences to astronomy, or you name it. So background of this particular project is what we want to do is to monitor and predict bird movements, because there are two problems: biodiversity threats, so we just want to know how they move, where they move, and also because of collision with traffic. It's quite a problem, and crashes happen because bird flocks are appearing in some places were not identified, and we really want to know where they are and take decisions in a timely manner. So far, ecologists do rely on citizen science, which is to say, some people are observing some, birds, and they report saying, "Oh, I've seen here, I've seen there." So this is what is happening. Individual tracking is also being used, and bird radars. I must say I'm not a specialist on the domain. I know what I need to know for this project, but bird radars are just a specific type of radars which are used to track birds up to 2 kilometers. Okay, so that's compared to weather radars up to 200 kilometers is quite a difference. So therefore, we cannot use this data for long-term monitoring. Now, scientists did realize that meteorological radars can fill this gap. But the problem is that, according to literature, so far, solutions are only on a coarse scale and only two-dimensional projections. So radar data is three-dimensional. And I'll have a slide on it a little bit to give you understanding what the kind of data it is. But solution so far has been focused on two-dimensional. So basically what they did, they took a three-dimensional data, they projected on a plane and made PNGs out of it, like images, and feed it into CNNs, convolutional neural networks, and that was it. So we basically lose one dimension, which is not ideal. And the question is, we want to find solution to this problem using a 3D approach, which is not trivial. So questions we were kind of guided by, or scientists we work with, the questions they are asking is, can large aggregation of birds or flocks be identified with this type of data? And we want to be using three-dimensional, all three dimensions there. And follow-up questions which are on the way still, can these birds be tracked as well? So can we add this temporal dimension and track in time where do they move? Okay, so just because I talk a lot about meteorological radar data, just to tell you how cool it is, because for me it was new, kind of new. I only knew we could see when rain is happening, right? But it's not all you can see. You can also see different type of objects. You can even identify insects if you want to. Imagine, like, I was completely surprised by that. So basically there are two types of radar data. So kind of old type, which is you can see here on the top, which is basically only can identify like horizontal electric field waves, okay? And there is a new one, I mean, it's not new from this year, but it's relatively new, which is called dual polarization radar. So it has vertical and horizontal waves. And because of that, you can identify also shape of the object, density of the object, a lot more features that you otherwise wouldn't be able to. So we can say whether it is snow, whether it is rain, whether it is a bird, or maybe insect, or boats, or waves, anything it's reflected onto. So for this project here, like just to move on, so on the right side, you can see example of reflections in one of the radars in the Netherlands, which is based in the north of the country. And you see timestamps, like every 2 minutes, you have like you can get the image by looking one of the features. In this particular case, it's reflections. And you can, you as an expert, I'm not an expert, but the expert can look at it and can see, oh, this reflection is in this particular range, it must be biology, it's probably a bird. So this is how they do at the moment manually, which is of course not the way we want to go. So just to conclude on this type of data, so we can detect scattering from all moving objects, okay? And sometimes also on the ground, could be traffic, you can see boats, you can see waves, if it's kind of reflecting on the bottom. We can distinguish birds from rain because of their movement, they move from bottom to up. And we can find properties such as densities, shape, and spatial variability. So basically, it's kind of whole range of data you can explore. For our particular problem, so we have 120 scans. Well, I say scan, this is how I understand it, but in their language, they call it polar volume. So polar volume, it's like 5 minutes radar is taking to scan whole thing, and then it goes again and again and again and again, over and over non-stop, and all data is freely available, so you can imagine the amount of data. But the problem is that this data is not annotated. So we need a person to make sure that we know what is what, so we can use this data in some ways. In our case, we did manage to get 120, so we just bugged our colleagues in Christmas time saying, can you please annotate? And they were annotating for us, but this is as far as we could get. Like human, it's quite intense, you cannot really do more than that. So original approach for us, we were thinking, okay, maybe we can do something with point cloud data because there are a lot of applications already out there. But we cannot, because if we go with this point cloud approach, we only have 120 points. Okay, so what kind of deep learning or machine learning tool can cope with that small amount of data? So instead, we decided, well, what if we go creatively and we present our data as a graph? And I'll show you graphs are so cool, almost anything can be presented as a graph. Like our room and our connections here can be a graph, and you can do all cool stuff on it. So by presenting as a graph, we approximately managed to create about 1,000 graphs per polar volume. I say approximately because depending on the settings. So this is, I tried to visualize approach we took. So first of all, we had this input data, which is, point cloud data. Point cloud data, by the way, is not a raw data type coming out of radar, but it's easy to generate it. There is a software for that. So you get the point cloud data. After that, we said, okay, so for every labeled point we have, we call it point of interest. It's either 1 or 0. We say we look at the number of neighboring nodes. Okay, so if there are enough nodes, in our thinking, well, if it's a bird flock, so there is more than a bird, there are a few of them, but it can be anything, it can be any object. We say, okay, select those. But at the same time, we faced problems that in some cases we had too many of them. So we said, well, if there are too many, take a random sample and just limit to the same number. So here comes the second condition. We say if maximum number of points of interest is more than a particular number, well, we said 200, because these numbers are guided by our use case. But if you think of any point cloud data and you want to generate graphs out of it, it will be your use case and you'll be setting your numbers according to your problem definition, just because we know how big flock can be, how fast they fly, etc. So then after that, we get basically by selecting these points of interest in red and neighboring nodes, we say, okay, so from here now we want to create edges. But again, we want to say we only want the ones which are connected to each other. Okay, so we create edges, and in this particular case, we get one graph. And this is how we produce what we call data sets out of point cloud, and approximately, I say approximately 1,000, because it depends on the configurations. For specific, like all the specifics are on our Git repo, and I provided link in the description, but also over here you can have a look at how it is. I'll go a little bit quicker through this one. This is just example of features we included, but again, it's just a vector you can provide for your specific use case. Here we say, well, look, let's have a look at elevation, at range, and some reflectivity parameters, and the difference between signal strengths, etc. So there are many different features which could go in there. And now we came to GNN part of it. So as I said, graph neural networks are just type of neural networks which operate on graph structures. Okay, I hope you've seen now what graph structures are, just nodes connected with edges, in the basic representation. There are different types of prediction tasks which you can do on graphs. You can do at the graph level, so you want to say something about graph on its own. You can do on node level, and you could do at edge level. In our particular case, we work on a graph level. Okay. So what we want to say is that this point of interest is this one dot with neighboring nodes around it. Is it a bird or not? This is a question we are phrasing. More specifically, there are different types of graph neural networks again. We use convolutional graph neural networks. So it's kind of convolutional in the sense that it's very similar to convolutional neural networks in the sense that in there we use like a filters and we slide around and we collect the neighboring information. In the graph neural networks, in this case, we have nodes, and we make use of knowledge of neighboring nodes and their feature vectors to collect information to the center node. So in its basic representation. And there are different strategies for summarizing data. It could be mean, sum, attention, graph neural networks, whatever. We use the mean one. And by by constructing a deep neural network, we can propagate information through the layers and capture complex relationships. Basic architecture, we're still working on it. I can just tell you at the moment, so we, out of the box, as we provided kind of, as we finish programming, and out of the box we get 90% accuracy, just to tell you that graphs are amazing. Now we moved up to 96%, and we are wondering, can we do better than that? People say, no, you can't, but we are still hoping. So at the moment, what we see is, in our particular case, but it's quite flexible, so if we write it as a package, obviously, so you can provide different inputs. In our particular case, we have three convolutional layers. We integrated different possibilities for activation layers, and output would be, basically identification problem, classification 0 1. In terms of implementations, just a few notes to note. This is all now in the code. We evaluate model on one graph, just using stratified coupled cross-validation, just to make sure that our model doesn't depend on one graph only, or one kind of influential graph. We evaluate model on polar volumes using leave one out cross-validation. What is interesting to find that major improvements we noticed in our graphs is, in our algorithm, is when we used step decay of the learning rate. So what it means that learning rate was changed after some number of epochs we specified. So once we said, can you adapt it according to number of epochs, so we don't use the same learning rates through the whole process, but we adapted, we got really good improvement in the model, like by about 5% maybe. as I'm running out of time, just the last slide here. This is first outcome from our model on biology. This is yellow and green. So this is our predictions. This is how it looks like. And the expert, who is not me, but my colleague, he is comparing with some feature, and he's able to say, well, what we see here is, is good or can be improved or whatever. So this kind of tools will be available to scientists. And we also, I know, just to finish up, it might be a strange thing to say, but we also write like interface for R users, because unfortunately a lot of scientists still stuck on R, and we want them to be able to use it, so they can call Python package through their R and do these calculations. And I think I'm done with it. Thank you so much.
Thank you, Olga. We will have time for questions.
Hi, thank you for a very interesting talk. Have you investigated how sensitive the model is to how you construct the graphs? So you mentioned that you sort of create graphs if points of interest are below a certain distance to each other. Have you tried changing that number, for instance?
Yeah, we spent a lot of time playing around with those numbers. First of all, we are guided by domain knowledge. So what makes sense? Can we expect bird flock to be of that size or not? So that's the first principle we did. And secondly, of course, we changed. It's mostly it's kind of time consuming at the pre-processing stage. To produce those 1,000 graphs per volume takes a lot of time. So we did run through optimizers and profiling just to see what code is doing and how quick it goes. So it's a big issue actually. It's a good question.
Thank you.
Hello, thanks for the interesting talk. I have a couple of questions. First of all, you said initially that you have problem with annotated data. So I guess, did you try some clustering techniques there to get?
Yeah, so what our project colleagues are doing, they basically open up, like on the slide here you could see, they open up one of those, like they look at different features they know that are responsible, because there are some, there is a lot of documentation on how to identify biology from this kind of data.
Yeah, actually,
so,
can you explain it? Because
I can explain as much as I understand myself, because I wasn't annotating myself.
Yeah.
So they open, for example, this DBZH, it's like reflectivity. And they look at a particular range of values. For example, if they are falling between, I'm just saying, 35 and 45, and at the same time this particular something else, then it is likely to be biology. So what they do, they have like a visual tool, they just draw polygons around saying, oh, this is all looking like a flock, get it done. Pick another one, oh, this looks like a flock. I know, like, so data is quite clustered, so if you have a point of interest, you're likely to have a lot around it. And in some cases it can be quite dense, that's why we said, well, let's subsample, because otherwise we're stuck on the algorithm, yeah.
Yeah, but eventually you just used the annotated dataset, I guess, right?
So yes. So after it was labeled or annotated, we used it as an input in.
The GNN.
Yeah, I think it's about. I might be wrong. About 50% of data would be NAs, like missing, so to speak, that we didn't annotate it, and we have kind of thing for that to handle that as well in the code.
Nice. And how do you select the? And how do you select the range to build the graph from the points in the point cloud?
Well, we have like parameters set up for that, so you could.
Play with it.
Yeah. Well, we provide defaults, the ones represented based for our problem. But if you have a point, is that what I'm saying? If you have a point cloud data and you want to make a graph out of it, you could use the same. You just need to adjust values for your use case.
Okay, and one final question. Thank you very much. So the output of your model is whether it is it's binary, the probability of.
Well, at the moment, we only predict bird or not, but what they want is to predict also whether it is a wave or a sheep or a traffic. It's just multi-classification problems then.
That's my question. What else can it be? Because it can be rain, snow.
Yeah. You can do all that. At the moment, we only have 2 classes, but it's easy to extend to 5 or whatever. Yeah.
Okay, thank you very much.